When it comes to MiECT, as a perfusionist, I think it's very important to talk not only about patient outcomes, but how safe are the devices to actually use. So the objectives of this presentation is to review the safety of MiECT from a technological standpoint with regards to the perfusionist and the team. When trying to adapt new technologies, one of the things we often take for granted or don't necessarily see when we go on observations is the time, effort, and thought processes that have made this procedure successful. I like using the analogy of my 8-year-old son, who's now 22 by the way, steering a boat. If we just focus on him, we do not get the whole picture. The picture of his safety device, his grandfather being ready to act in case my son does something he's not supposed to. In the same manner, although most pictures don't show it, MiECT systems have been designed with the utmost regard for patient safety. One of the big concerns is the air handling. How well can MiECT systems actually handle air coming down the venous line? If you look at the algorithm for venous air during conventional cardiopulmonary bypass, air comes in the venous line, you have to lower your flow, walk the air out, fix the problem, and then recommence circulation. Basically, there's no difference in using a MiECT system. It's the exact same procedure. However, the air is just removed automatically out of the venous line. But you still do the same thing. You see venous air, you decrease your flow, air is removed, you have to fix the problem and commence your circulation. To help achieve this, with the exception of a type 1 circuit, all systems have a bubble trap in the venous line. This is all part of a greater air purging system. Venous air comes down the venous line, hits a bubble sensor, which then basically triggers an air purge pump to take that air off the circuit. The air purge pump will stay engaged until both sensors do not sense air anymore. A third bubble sensor is after the bubble trap, and if that detects air, the centrifugal pump will go to 0 RPMs and the arterial occluder will occlude. Basically, all systems are very similar. Medtronic does it a little bit differently. They have an ultrasonic air sensor in their bubble trap, which basically is, once it senses air, a vacuum source will then pull that air off. How effective are these? Well, we did a little study back in 2018 and compared conventional versus a MiECT system. So we delivered air down a venous line by using a gas blender. So the air was entrained, set at 1 liter per minute, and this is how much air you can see being pulled off by the bird. So in a controlled lab setup, we compared conventional cardiopulmonary bypass to a MiECT system with a blood flow of 5 liters per minute. The hematocrit was 26% on these circuits. Sweep was 2 liters per minute with an FiO2 of 100% and blood temperature at 36 degrees Celsius. For the conventional system, we had 200 mils in the reservoir, which is the minimum operating level, and we ran 3 of these systems. Just to look at the schematics, We use a spectromonitor to actually measure air emboli. So we used one before in the venous line, before the VARD or the venous reservoir, after the pump in both situations, and after the oxygenator. What we found was at 0.4 liters per minute, the MiECT system had a few more emboli than the conventional system pre-oxygenator, but at 1.2 liters per minute of air going down the venous line, the MiECT system had much less emboli count pre-oxygenator. And post-oxygenator, there was no air detected in either system. This just confirmed the results of Perthel and his group when they looked at air handling of MiECT system and found that there was a lot less air in the arterial line in the MiECT system compared to conventional cardiopulmonary bypass. So another safety feature is the auto ramp down feature. So again, as part of the venous air algorithm, if you start seeing venous air, it doesn't matter if you're in conventional cardiopulmonary bypass or MiECT, you're going to decrease your blood flow. So the auto ramp down feature in MiECT basically decreases the flow for you. If the bubble sensor detects air coming down the venous line, the RPMs of the centrifugal pump will automatically be lowered to a preset point. This will allow you to react to evacuate the air from the venous line, decreasing the probability of overwhelming that venous bubble trap. Another safety device that is used often during MiECT are automatic clamps. Automatic clamps are used in conjunction with bubble sensors. So if the venous bubble trap gets overwhelmed with air, the bubble sensor will detect air, and at that moment will cause the clamp to engage and shut the circuit off from the rest of the patient. It'll close automatically when air is sensed by the bubble sensor, obviously, if there's retrograde flow, if flow goes to zero, or it also can be engaged manually. Anyone who has run MiECT cases know that flow is very sensitive to the volume status of the patient. Loss of blood can cause increased negative pressure in the venous line, resulting in cavitation and decreased blood flow. We often see this when diverting blood away from the patient, either through a vent, cardioplegia, air purge control system, etc. Spectrum, through their quantum heart lung machine, has integrated a volume pump to help manage these shifts. A pump is placed between a blood collection reservoir used to collect vent blood or blood from the air purge controller and the venous line. So if you're using an open reservoir, you can use level sensors to control the pump. If volume in the reservoir meets the yellow level, the pump will be triggered to turn on and automatically give volume into the venous line until the reservoir reaches the red detector, where the pump will actually stop. You can also turn the pump on automatically to match vent blood or cardioplegia flow. For a bag or closed reservoir, you can set the pump to activate based on the negative pressure in the venous line. Centers that use a Type 4 MiECT circuit have the capability of performing a Bailey procedure. An open shell reservoir is placed in the venous line and clamped out during the case. If there's air comes in to the venous line, or for some reason they need to convert, all they need to do is take the clamps off, here and here, and clamp the venous line here, and then they have a total open system, which they can use with either gravity assist or vac assist venous drainage. Then once the problem is cleared, then you can revert back to MiECT at that time. One thing is clear, with any cardiac surgery, teamwork is essential, and this is no different for MiECT perfusion. I think as a team, to progress into MiECT, there are certain things that need to be prerequisites. You need to be used to sequestration of suction blood, retrograde priming. You need to be using coated circuits, centrifugal pumps, and you definitely have to have emergency training. And I think all of these are prerequisites before attempting any advanced technology. We know that the more training you do has a very high impact on patient safety and quality of care. Training should be in multidisciplinary teams consisting of cardiac surgeons, anesthetists, and perfusionists. There should be practice on simulators and wet labs in order to promote continuous education. I think the best way to start any program is initially start with 2 perfusionists per case, because it doesn't matter if you're pumping the case or you're just observing, you still learn a lot with these MiECT systems. And then once you get used to running these cases, staging yourself, first doing coronary bypass surgery and then progressing into aortic and mitral valve surgery with these cases is probably the best way to approach it. So I'd like to conclude just by saying, with appropriate preparation and comprehension, MiECT can be easily adapted without compromising the safety standards that we, the cardiac surgery team, are accustomed to with conventional cardiopulmonary bypass. Thank you very much for your time.